Hey, today I'm going to be explaining what neural networks are. We're not going to go into too deeply as to the mathematics behind it, but you'll build the necessary mental models to actually start working with this technology in tools like PyTorch or Tensorflow. Now, the topics that we're going to be covering are the basics of a neural net. So this includes the three layers that go into building a neural net, and you'll understand what a layer is and what a neuron is. We're also going to be explaining what weight, biases, and activation functions are, and how they help in the job of a neural network. Then you'll be understanding how these three things are used in computing the new neuron's value. Because each of the neurons in the previous layer, essentially, and again, you'll understand this more when we explain what a neural net is, but each neuron in previous layers are actually used to compute the values of new neurons because information is passed from one layer to another. Again, you might not understand that right now, but once you backtrack to this part of the video, after the video is done, you will be able to easily understand what I'm talking about. Then we will be talking about backpropagation, which is an algorithm that is used to actually train a neural network. Because if you have some familiarity in AI, what happens is we have training data sets, and these training data sets capture the statistical pattern which is present in those sets. And now, using those patterns, you can actually predict new things and novel things. And that's exactly what's happening within a neural net, specifically through backpropagation, which is actually used to update the values of the weight and biases. Because by default, the weight and biases, which are just numbers which are multiplied and added to find the value of the new neuron, they're random. But through backpropagation, and specifically using the loss function and optimizer function, they are updated iteratively. And we're going to see that more in detail when we get to that topic. And this is just the diagram which we're going to be using, right? So you notice how I was talking about layers. There's multiple different layers. And in the next section, I'll explain exactly what is happening in this diagram. Okay, so to start off, I want to explain what a neural network even is. And it's an AI model which captures statistical relationship given a training data set, and you can use that to predict what the outcome or output would be. Okay, and that's based off of a given amount of features or inputs. So, for example, let's say you have a neural network which predicts housing price. So in the input, the amount of neurons that you have are the amount of features that you want to input into it. So the amount of data that you want to input. So for example, you could have things like square footage of the house, the amount of bathrooms in the house, if you have a basement in your house, if you have pets in your house, right? Again, it doesn't really matter what data you input into the neural network. It just has to be related with the problem that you're solving or the problem that you're actually predicting for. In my case, it's related to housing, so I just gave metrics around housing. These input layers then go through a combination of hidden layers to finally give you an output. And in the output layers, you have just the outcomes which are possible. Now, each of these layers are just a collection of neurons, okay? And the three foundational layers are the input layer, the hidden layers, and you can have multiple hidden layers. Not 2, not 3, not 4. There is no set amount. It just depends on the complexity that you want your neural network to take on. And depending on your task, you could have like thousands of these even. And then you have your output layer, okay? Now, the value that you get in your output layer is going to be unnormalized or raw. You can think of it as just not processed yet. It's just the output that you get. So what you can do is you can actually take that values and you can pass it through something called a softmax function. And this actually happens in LLMs which use neural networks, and specifically a architecture on top of neural networks called transformers. But at the foundation, at its core, it is just a neural network. So what they do is once the neural network goes through the processing, right, and you have your final output, they pass it through a softmax function, which actually creates a probability distribution. And a probability distribution essentially allows each of the outcomes, in this case you have two outcomes because you have two neurons, each of these outcomes have a slice of 100%. And the more that you have of this slice, the more probable that outcome is given the inputs that you have actually put in. Okay? So just to conclude, the basic components of a neural net are the input layer, the hidden layers, and then the output layer. And each of these layers is just a collection of neurons. Now, a neuron itself is just a unit which allows for computation to happen, okay, or mathematics to happen. Because really, the neural network at its core is very simple. It's very dumb. It just does multiplication, addition, and parsing it into a function, and that's literally all the mathematics that goes into it, right? But if you stack these hidden layers, so much, it would add so much complexity that it will be able to actually model very complex patterns. And so that's the power that goes into neural networks. And again, remember that neural network is just an AI model which allows you to predict things. But it's unique in the sense that it's actually modeled around the human brain. Just like we have our own neurons, and these neurons are interconnected with one another, each of these neurons are interconnected with one another through these connections, or channels, as you can call it. Before I delve into the specifics of what weights are, it's important to understand how the relationship between these neurons actually occur. So I want to build sort of a mental model behind this. And to do that, I'm just going to be focusing on the input layer and then the hidden layer, okay? But what I say right now applies to any layers or any sets of layers. Now, what happens is information from the input layer is passed in a one-way street to the hidden layer 1. And this is applicable to all other layers. No information, when you have finally trained your model, no information can go from the hidden layer 2 to the hidden layer 1. It just doesn't work like that. It's all forward pass, okay? In fact, this process is called forward propagation, which just means information moving from one layer to the next, okay? Now, each of these neurons have a channel or connection with every individual neuron in the new layer. Which means that, let's say this is neuron A. Let me actually write it down. So let's say this is, oops, that is very thick. So let's say this is neuron A, okay? This is neuron B. And this is neuron C, okay? Very simple. Now, neuron A has a connection or a channel with every single one of these neurons. So every 4 of these neurons. The same holds true for B and C. That's why you see that even though this is a very simple example, there's not that many neurons happening here. You can see how many connections are made. And that's where the complexity lies, right? All these connections hold some sort of pattern or meaning, right? Which is modeled through the weights and the biases. So if you have so many of these connections, it'll be able to capture very complex and nuanced parts of the data set. Okay, now that we understand that, what exactly is a weight? Well, a weight actually encodes the importance of the information from the previous layer to the new layer, and specifically the previous neuron to the new neuron. And to show this very specifically, I actually have a diagram here, okay? So you can think of this over here as your new neuron, okay? So I'll actually write it down. So this here is your new neuron from the new layer, okay? And these are the previous neurons from the previous layers. And you'll notice that each one of these has a channel or a connection with your new neuron. And each of these connections has a unique associated weight to it, which is actually representing how important the information from this neuron is with your new neuron, okay? Now, you'll notice that there's a lot of complex math here, or it looks complex, but it's not really. And I'm going to break it down. So to start off, I would like you to ignore the function here. This is the function notation, right? The F over here. Ignore that, because that has to do with activation functions, which I'll explain later on. Ignore the B here too, because that's the bias. All you need to understand is this over here, okay? And this is what we call the summation notation, which just means that essentially what's happening is that the values from these neurons, which are represented by X and a subscript, are multiplying by the weight associated with the connection between that neuron and the new neuron, which is just the weight and then a or W I should say, and then the subscripts. So that's all that's happening. You're multiplying the weight by the previous value, and then what you're doing is you're adding this value that you get with all other values for all other neurons. Because remember that the relationship is modeled in a way that each one of the previous neurons has a relationship or has a connection with a new neuron, which means they have their own associated weight and their own associated value, which gets multiplied. So then all these values or all these products are added together so that they're actually being able to be passed into the activation function, which is what's happening here. Before we go into what a bias is, I think it's very important to understand what an activation function is. And to do that, I actually have a Reddit post which actually explains it very beautifully. But before that, there's some context you need. An activation function introduces nonlinearity in your neural network. By default, your neural network is essentially just these lines, which are just manipulations of multiplication and addition. And you're just adding all these lines together when you stack these new layers. So when you do that, you're not going to actually get a nonlinear relation, right? You're going to get a linear relation, because if you add a line on a line, you just get a linear relation. So by adding this activation function, you're introducing a nonlinearity. And by doing that, when you stack on new nonlinear lines, you're going to actually create different patterns, and these patterns will be able to model more complex relationships, which actually creates meaning and a reason for why we should even stack on more of these neuron layers. And as he explains it over here, this Redditor, if you add a line and a line, what do you get? Another line, right? That's what's happening without the activation function, because it's just a series of operations that are being added and multiplied. And any linear combination of linear functions results in a linear function. Exactly what he said in his first line, just explaining it more mathematically. And so if you have these like series of linear relationships, you can actually model a nonlinear relationship. And many of the real world complex patterns are nonlinear. So this activation function just allows you to produce nonlinear relations. In conclusion, real world patterns involve a lot of nonlinear patterns. And by default, the neural network does not include nonlinearity because it's only multiplication of weights and additions of biases. So by introducing this activation function, you actually add nonlinearity to model complex relationships. Very simple. Now, the most commonly used function, because there's multiple activation functions that you can use, but the most common one is rectified linear unit, ReLU. What this does is, it's very simple. What it does is that it outputs a positive, if your value is a positive, it outputs that input. Otherwise, if it's a negative, it returns a 0. Again, this is by default. So, for example, if you have a value of, let's say, 5, right? That's the value that you get after you add the bias and then you add all of the weights together, the weighted sums together. So when that equals 5, it's a positive value, which means for the rectified linear unit is just going to output 5. So the value that the function gives is going to be 5. However, if, for example, let's say when you do all of the computation, you get -4, then it's going to output a value of 0. Okay? So that's sort of how the rectified linear unit works. Again, this is just one of the many that are used. You also have something called the sigmoid function, which uses a different method of producing nonlinear values. But what really matters in understanding activation functions is not necessarily the internals which go around in the rectified linear unit or the sigmoid function, but rather it's just that they introduce nonlinearity, which helps you actually make the model useful, because now it's able to capture more nuance and more data points. Now I'm going to explain what a bias is. And to put it very simply, a bias shifts or updates the final output that you're going to get in your activation function. And it does that by actually taking that value and manipulating it by adding it with the weighted sum, which is then passed into the activation function. And this is needed because the patterns in the real world have built-in natural tendencies, right? For example, you might have a natural tendency to prefer the cold over the warm, right? And so these natural tendencies need to be modeled within the relationship that you are making with your new neuron and the old neurons that were in the previous layers. And that is captured by the bias, right? You can think of it as the actual bias that you have in your real life. To conclude, the bias is a way of shifting the output that you get from the activation function, which becomes the value of your new neuron. And the reason why we do this is because real world relations have built-in tendencies which will affect the output or the decision that you make. And the example that I gave was for temperature, right? For example, if you have a natural tendency for the cold, well then when you're actually going to be picking a preferred temperature, you're probably most likely going to pick a more cooler temperature than a warmer temperature. In the same way, this bias would allow for this preference of cooler temperatures to be modeled through adding some sort of value into your weighted sum, which then gives you an activation function. Your activation value, I should say. And remember that a singular activation value means nothing. It's a series of these biases which are added through these weighted sums, and you have these thousands of neurons. It's then that they actually become meaningful. So one value on its own, or one computation of this multiplication and addition of weights and biases, means nothing. It's when you stack them in these layers that they actually are able to produce meaningful values. That is pretty much the overarching understanding that you need to actually start working with neural networks. Again, this is a very bare bones example and a bare bones explanation, but it's enough for you to now actually start diving deeply into TensorFlow and how exactly you can build these architectures yourself and use them. So I highly encourage you to now take this information and actually apply it in some sort of project. And personally, I use TensorFlow, so I'll definitely recommend you to use this this library when building your neural network.